Hi, and welcome to my YouTube channel dedicated to my HO scale Santa Fe layout set in Texas, 1993. It's an operations-focused layout based loosely on the Slayton subdivision and Lampasas subdivisions in West Texas. In a bit of a divergence from my other videos, I want to talk about planning for operations, or more specifically, developing an operations plan or a schedule. This is part one. Part two, I'll talk about operations on my layout, or what my operating plan looks like. If you were to ask me what the most enjoyable aspect of the hobby is, I would answer operations. Sure, I enjoy operating and training with a purpose, but developing an operations plan has been the most enjoyable part of the process for me, and I want to share some of the concepts that I followed in planning for realistic model railroad operations. This video is a guide on how to get started in model railroad operations, and it all starts with a plan. You'll find that there's a little bit of something for everyone, whether you're in the dreaming stage, new to operations, or maybe you have a lot of experience in the hobby. I think there's a little something for everyone. I'll walk through some of the most important considerations I made and how I developed an operating plan that to me is both realistic and rewarding. Remember, this is just a guide. I'm going to keep it very high level. I'm only sharing what has worked for me. At the end of the day, it's your railroad. One of the first things we have to decide in model railroading is what our goals and objectives are. Operations may or may not be part of that. I think one of the reasons the hobby is so interesting is that for every individual modeler, there's probably a unique set of goals and objectives, especially when we consider time and space in the equation. Generally, we can define our railroads as being prototype-based, freelanced, or a combination of the two, often referred to as proto-freelanced. We can strictly follow the prototype, develop our own fictitious railroad, or we can combine both elements. Regardless of the path you choose, geographic location is going to be the most significant driver to the purpose your railroad serves. To develop realistic operations, we first need a purpose. Is your railroad part of a major Class 1 railroad, moving traffic great distances? Or is it a bridge line moving traffic to and from a major railroad? Maybe it's a regional railroad, or perhaps even a short line or a narrow gauge line, or logging railroad. By setting a geography and type of railroad we are replicating, we can now start to identify the train types that would regularly operate in your area. Part of the fun here is researching the traffic and the traffic patterns. For instance, because I model Santa Fe in the early 1990s, hotshot piggybacks and double stacks would be staples on my main line. Aside from intermodals and the usual mix of regular manifest traffic, grain trains would be a commonplace in my version of Texas. If you're going to follow a prototype, you'll need to do some research to know the train symbols of your era. This can be a lot of fun, and along the way you can really help visualize what the layout and rolling stock might look like. You can still incorporate all of these steps if you're freelancing as well. Identify each train type that you'd want to represent on your layout. Depending on your location and routing, it's quite simple and realistic to add numerous trains of any type you want represented. Once you have a general idea of your traffic base, you then need to consider how this fits within your railroad space. More specifically, how many and what trains will operate on a day-to-day basis. Notice I didn't say daily, and that's because a railroad that operates on the same schedule 7 days a week is far from the norm. Even if you have a prototype schedule available to you, you will have to design your own schedule that fits your railroad. Schedules, or maybe more prototypically operating plans, will depend on the space required for your track plan and must always consider time. The class or condition of your trackage will dictate your operating speed, and that is the common denominator of making your operating plan. It really is all about the speed you operate. If your layout is mostly Class 1 main line, prototype speeds will be much higher than, say, for example, a branch line. The one thing we have to consider here is that time does not care what scale you model, only the space you model. Time doesn't reflect the scale you model, but distance is always going to be a factor. Here are a few major considerations when making a workable operations plan. At the very basis of operations, we need to measure the time it takes for a train to traverse the entire layout at what seems like a reasonable speed. I like to then take it one step further and reduce my speeds by another 1/3 or so. For example, my throttles run with 28 speed steps. And even after programming the locos to roughly 75-80% of their CV5 or maximum speed value, I instruct operators to use mainline speed limits of step 18 to 20, and only in the case of intermodals would they ever exceed speed step 20. Using whatever speed you deem appropriate, operate your train from one end of the layout to another. For simple math, let's say it takes 10 minutes to complete the journey. Now that you have a good handle on travel time, let's focus on the actual representation of time. For operating sessions, I'm a big proponent of having some form of governing fast clock. Sure, you may have a layout that can be operated in real time or a 1-to-1 ratio, but typically model railroads geared towards operation will be run on a fast clock, whereby the clock advances at a predetermined speed. Typical ratios in model railroading are 3-to-1, 4-to-1, 6-to-1, 8-to-1, 10-to-1, and 12-to-1. If we take a 6-to-1 operating ratio, which is what I have settled on for my layout, that means a typical 24-hour day would take 4 hours to complete. If we were operating on a 4-to-1 ratio, a 24-hour day would take 6 hours to complete. I find that with larger layouts, a ratio in the 3-to-1 to 8-to-1 range tends to work well. Smaller layouts might benefit from a faster clock, which makes the appearance of various railroad jobs taking a more realistic time to complete. The goal with a fast clock is to move the required trains realistically within realistic time constraints. If we take that 6-to-1 ratio and figure for a train to traverse a layout, it takes 10 real minutes, that would equate to 1 hour in operating time. We also have to test this ratio for something we think might be appropriate when we have to consider the time required to perform various switching jobs. A layout that requires a lot of switching would typically benefit in the same way a large layout would from a lower ratio. To put it simply, there has to be enough time for yard crews to build and receive trains without too much delay. If the yard crew is building a 20-car train and it takes 30 minutes of real time, the fast clock ratio would dictate that time in fast hours. Using that 6-to-1 ratio again, it would take 3 hours in fast time to build that 20-car train. Maybe that is acceptable, maybe that is not. Again, layout size and traffic pattern will be the driver here. It's the ratio that works for what you need to do to move the required trains realistically within realistic time constraints. The last thing that I would consider in the selection of a fast clock ratio is the distance between towns on a layout. The distance should also govern maximum train length, but that is an entirely different topic. If we actually look at scale miles, 1 real mile of 5,280 feet would convert to roughly 61 feet in HO scale. Even an operating main line of 200 feet only represents a little over 3 miles. That is the exact situation on my layout. So we have to selectively compress our layouts, the numbers of towns, the sizes of the towns, and ultimately the ideal train length. If we can satisfactorily compress our layout and incorporate some running distance between towns and terminals, we can then get by with a lower fast clock ratio. A smaller layout with more dense town network would likely benefit from a larger ratio. Back to the second point, switching takes time. So the ideal fast clock ratio is going to be whatever allows you to get all of your required trains across the layout and provides sufficient timing for switching operations within the space provided to you. Developing an operating plan using schematics. Once we have our fast clock ratio, we can now start to visualize our operating plan. I achieve this through schematics or string charts, and I'll provide some basis on this for you. Just a word of caution though, as you work through this, you may learn that your fast clock ratio will need to be adjusted. This is a fun way to test your planning process to the point. To develop an operating schematic, start with a large blank sheet of paper or utilize some sort of spreadsheet software. I prepare the software application for ease of modifying lines, copying lines, adding lines, and deleting lines. Start by laying out a full day on the x-axis or the horizontal axis. I recommend doing this in 15, 30, or 60-minute intervals. What we are doing is making a grid with equidistant points on the x-axis. Then we lay on the y-axis. This is where we're going to lay out all of our terminals and towns, including staging. Even if our layout is a loop, we have to think of this as a point-to-point system. For railroads operating east to west, I like to start with the easternmost point on the bottom of the y-axis and label this adjacent to the intersection within the hour 0-100. Then, place towns, etc. on the y-axis moving up or westward. This would be the same with north and south. In reality, you can do this however you like, but the most important thing is spacing your towns properly along the y-axis to reflect relative distances between points. You can simply get these distances by physically measuring your track lengths and reflecting them on your y-axis accordingly. For instance, two towns that are 30 feet apart would appear as closer points than two towns that are 50 feet apart. We can now start to lay our trains on the schematic and generate an operating plan. A few helpful things to consider are color coding trains by their priority and understanding that the more vertical the string line slope is, the faster that train is traveling. This typically meshes well with a higher priority train. Rising slopes, in my example, will be westbound trains, and falling slopes will be eastbound trains. Before laying our trains out, let's reflect back on step 2 and consider that time required to move a train from one point to another. We settled on a nice round figure of 10 minutes. If we go back to our 6-to-1 ratio we have initially agreed on, it would take roughly 60 fast clock minutes or 1 hour to complete its run. This, of course, does not take into consideration slowdowns for meets, online switching, blocking, or yard time. So I like to start by placing the hot or high priority trains onto the grid first, as they are generally more straightforward and less likely to wait for an opposing train. Even still, you have to put a good buffer in for acceleration and deceleration. I like to add about 50% in as a buffer. So if it takes me 60 fast clock minutes to complete that journey, I'm now looking at 90 minutes. So we now know that the highest priority trains are going to take 90 fast minutes or 15 real-time minutes to complete their journey across the layout. Now, as we start laying strings out for our trains, and of course assuming we have enough traffic, we will start to see string lines intersecting near various points. On a double-track railroad, this is generally just a pass-by, but on a single-track railroad, this is going to provide a clue as to where trains are most likely to meet. These locations will need to have a passing siding. One thing that quickly becomes apparent is that lines usually intersect away from the grid that represents a town or a siding on the y-axis. Don't worry, this is a quick and easy fix, in that the lower priority train may have to hold at an earlier location and wait longer for the opposing train to clear. Or you can adjust the schedule a bit now that you can visualize what is happening through the day on your railroad. When we talk about meets, the lower priority trains will typically hold. That is not the case in all railroads, but for simplicity, we'll go with that and start there. Meets are represented on the schematic by a horizontal line on a particular train's string line. The The longer the horizontal line, the longer the train is held waiting. You can then use your x-axis to know how long that wait is. If a road switcher or local, or any train for that matter, is doing work on line, there would be a longer horizontal line representing the approximate time it would take to complete that work before moving along. Once all the trains are on the schematic, you will have a basis to form a schedule. Let's have a look at our string chart now and see what the trains might look like as they move across the layout. Starting with A, we have a red line that's moving westbound. It's on a steeper slope because this represents a high priority intermodal. There are no anticipated stops along the way because of its high priority. Next, let's look at B. That is a manifest moving eastbound from staging, and it terminates at Temple Yard. Along the way, it is anticipated or expected that this train will hold at Edgeview for 2 westbounds. Now, moving to the far right, we can see a high priority manifest moving east from west staging through to Temple, and then finally ending at east staging. That horizontal line at D represents the time it takes for that train to drop a block of cars and pick up a block of cars. Finally, let's look at E. That's the brown line. This represents a turn out of Temple that leaves Temple, proceeds to Edgeview, works Edgeview for 2 or 3 hours, then continues on to Slayton for a couple hours, returns back to Edgeview to switch out the trailing point industries, and finally back to Temple Yard. Now, coming full circle, we have to ask ourselves, does the fast clock ratio we started with still work? If it doesn't, that's fine. You can tweak it. If the 6-to-1 doesn't work in your example, maybe the 8-to-1 is a better fit, or maybe the 4-to-1 is a better fit. This will help us see a clear picture of what the operation is going to look like and the time that we're going to need to perform the tasks that we need to do. A string chart schematic provides an easy opportunity to add and remove trains based on one of the greatest variabilities in model railroad operations. That variability is crew size. The number of operators available for a session will determine whether you can run a full schedule or not. For instance, on my layout, I need 10 operators plus a dispatcher to run a full session. I can do it with 8, but crews are running with little downtime. In order to accommodate fewer operators, what I then can do is alter the day of the week, which would see fewer trains. For example, a Monday would be ideal for a smaller group, and Friday for a larger group. The simplest way to reduce crew requirements is to remove what I call interference trains. Interference trains are trains that go from one terminal to another with no work in between. They merely provide operational interference, hence the term interference. At the bare minimum, a session must include all the trains required to serve switching operations. These would be manifests, locals, transfers, and switchers on my layout. I can accomplish this with as few as 6 operators. Remember, on the prototype, even the best laid plans can quickly fall apart. Maybe the most prototypical thing about model railroad operations is the ability for things to fall apart quickly as well. Embrace it, it's railroading. If you can do that, I think you succeeded. I plan to follow this video up with another video focusing on my operating plans. But until that time, thanks again for watching, and look forward to putting more content out there for you.